Today, we're going to do something a little ambitious. We're not just going to talk about large language models. We're actually going to build one, right from the very first line of code.
So, let's dive in with a guiding principle from the legendary physicist Richard Feynman. You know, to really truly get the magic and the mechanics of modern AI, we've got to roll up our sleeves and build it ourselves. And that is our mission today.
For so many of us, AI models are these powerful but kind of mysterious black boxes, right? Well, our goal today is to crack that box wide open. We're going to move from just using AI to actually understanding its core components from the ground up.
So, where do we even begin? Well, before we can write a single line of code, we need the blueprint. We need to lay out the fundamental architecture we're going to follow.
The transformer architecture, which is really the foundation of all modern LLMs, comes in three main flavors. You've got encoder-only models like BERT. They're fantastic at understanding the context of a sentence. Then there are encoder-decoder models, which are great for things like translation. But for what we're doing, generating text, we are laser-focused on the decoder-only model. Yep, that's the architecture that powers the entire GPT family.
All right, our first practical step, and this is a big one. Computers, they don't understand words. They understand numbers. Specifically, they work with these multidimensional arrays called tensors. So our very first challenge is to translate our human language into these mathematical objects.
This whole process is called tokenization. It's really all about creating a vocabulary and then mapping every single character or word to a unique number. Let's see how this works with a super simple example.
And boom! Just like that, hello isn't a word anymore. To the computer, it's a sequence of numbers that our model can actually work with. Each one of those numbers corresponds to a character in our vocabulary. This is the fundamental bridge between language and machine.
Now, this slide shows a really crucial trade-off. If we tokenize by character, our vocabulary is tiny, which is great, but it creates these super long sequences of numbers for the model to process. On the other hand, word-level tokenization gives us shorter sequences, but what happens when it sees a word it's never seen before? That's why modern models use a clever hybrid approach called subword tokenization. It breaks down unknown words like explainer into smaller known pieces like explain and You kind of get the best of both worlds.
And check this out. This shows you just how simple the core logic really is. This isn't some mystical, complicated process. It's a Python class with an encode method. It takes a string and using a simple dictionary lookup, it spits out a list of integers. That's it. This is the code that makes tokenization happen.
Okay, so our text is now represented as numbers. We're ready. We are ready to dive into the absolute heart of the transformer, the attention mechanism. I'm not exaggerating when I say this is the single innovation that changed everything. So think about this. When a model is trying to predict the next word in a sentence, how does it know which of the previous words are actually important? You know, if I say, the cat sat on the word cat is probably a lot more important for the next word than the. How does the model learn that? The answer is attention, and honestly, it works in 4 pretty elegant steps. So for each word, we create 3 little vectors: a query, which represents what the word is looking for, a key, which is what the word has to offer, and a value, which is the word's actual content. So, step 1, score. The query from our current word looks at the key of every other word to score how relevant they are to each other. Step 2, scale. We just tweak those scores a bit to keep the training process from going off the rails. Step 3, focus. A math function called softmax turns those scores into probabilities, basically deciding where to focus its attention. And finally, we apply that focus to each word's value to produce the final result. It's like a data-driven way of highlighting what really matters in a sentence.
And here it is, that whole beautiful logic boiled down to just 2 lines of PyTorch code. The first line calculates the scores, that's our score and scale steps, and the second line applies that softmax function to get the attention weights. That's our focus step. We've just translated that whole complex idea directly into code that a computer can run.
But hey, why stop at just one spotlight of attention? This is where multi-head attention comes in, and it's brilliant. It's like having a committee of experts looking at the same sentence all at once. One head might be focused on the grammatical structure, another might be looking at the semantic meaning of the verbs, and a third is tracking pronoun relationships. By running multiple attention mechanisms in parallel, the model gets a much richer understanding of the text.
Okay, so we've got tokenization and we have our attention engine. Now it's time to put these Lego pieces together and build the fundamental unit of our model, the transformer block.
I really want to pause on this single line of code because, believe it or not, it's one of the most important concepts in all of deep learning. It seems so simple, doesn't it? We take our input x, we pass it through our self-attention layer, and then we just add the original x right back in.
This little trick is called a residual connections, and it is an absolute game changer. Think of it as a gradient superhighway. It lets information from the initial input flow directly through the entire network, basically bypassing layers. This simple little plus sign is what allows us to stack dozens, even hundreds of these blocks on top of each other to create truly deep, powerful models without the whole training process just breaking down.
And this table here, it shows you how we scale these building blocks up. To go from a base model to a bigger, more capable one, we don't necessarily just add more layers. Instead, we increase the dimensions. We make the model wider. We give it a larger embedding dimension, a bigger feed-forward network, and more of those attention heads to work with.
We've designed the architecture. We've written the code for the core components. Now comes the grind. Teaching our model how to actually understand and generate language by showing it a truly massive amount of data.
You know, the core of all machine learning is really this iterative loop. First, we grab a small batch of data. We run it through the model to see how well it predicts the next word. That's the forward pass. Then we measure its error, or what we call loss. Then we do a backward pass to calculate exactly how every single weight in the entire model contributed to that error. And finally, we update those weights just a tiny bit to make the model a little bit better. Now just repeat that millions and millions of times.
So after this super long pre-training process, what you have is a powerful base model that really gets the patterns of language. But here's the thing, it's not a chatbot yet. It's just a really good text completer. The final critical step is fine-tuning. That's where we train it on a smaller, much higher quality dataset of instructions and responses. This is the secret sauce that aligns the model to be helpful and conversational.
So we've gone all the way from a philosophical quote to a fully trained model. We've opened the black box. Now, let's wrap up with the essential takeaways if you're feeling ready to start your own building journey. Okay, first things first. You'll need some solid Python skills, especially with classes. Second, the hardware is way more accessible than you might think. You can absolutely start tinkering on a laptop, but for any serious training, you're going to want a GPU. And finally, and I can't stress this enough, never forget the cost of attention. Its complexity means that if you double the length of your input text, you don't double the compute time, you quadruple it. That is the #1 bottleneck you'll face when you're trying to give your model a longer memory.
We started with this idea that to truly understand something, you have to create it. You now have the fundamental blueprint for one of the most powerful technologies of our time. So really, the only question left is, what are you going to build?